Join me in welcoming to the Distinctive Voices podium, Dr. Yoky Matsuoka.
Well, good evening. Thanks for the introduction. I didn't realize that she knew that much about me. She took some of the words from the slides. This is fine, but that was great. And thanks for the introduction. And I am always kind of embarrassed to hear about myself introduced. And this MacArthur thing especially is, now everybody thinks I'm a genius, and I'm not. So I just wanted to make that note clear. There's the recent event that's funny that that happened to me at the airport. So I always travel with my kids. I came here with my 3-year-old twin daughters, and I had been traveling with my 1-year-old until he was done nursing. And last time I was traveling to Cleveland, somebody came up to me, or actually 2 guys were looking at me, and then they said, and then I thought, oh boy, I must have like spit on my shoulder or something. But and one of the guys came and said, excuse me, are you that certified genius? And I thought, well, I guess so. And he then yells across the whole waiting area and says, hey, dude, she's the one, she's the genius. So then now everybody's looking at me like, what is that? What is that? And we get it on the plane, and then we're all going up in the sky, and then the seatbelt sign comes up, ding, and then slowly people stand up and says, excuse me, I overheard that you got this award, and I actually have a question. And then actually line kept getting longer. It was really, really funny, but I have to say about 80% of the questions are something that you might think of the moment you hear the word genius. Was basically saying that, well, I think my kid might be a genius, so, what should I be doing? My son is 8 years old, and I think he's doing really good in math and science. Should I be putting him some AP courses now? Should I be doing something very different? I think those are the majority of the questions. And what I always answer to that, I just laughed and said, oh, great that you have a very smart, kid. But I, really believe in pursuing passion, whatever that might be. And it turned out for me was sport. I didn't even think math and science was important except for the fact that I did all right. So I just tell them, don't put them in some rigorous program that might sort of get boring and then, just get burnt out too soon. So that was always sort of my answer. And that was the lead on to my sort of the photo of me, of where I really started. So as Susan said, that I really started as a dreaming of becoming a tennis professional until my body fell apart and just didn't let me. And at that point in college, I was already in college. I was 19 years old, still dreaming to become a tennis player. I decided that maybe what I really want to do to, retain the tennis part of my life is to build this tennis buddy. So this is a recreation of what I have drawn up at that time of building a tennis buddy that I can tweak a button. On the days that I'm kind of tired, maybe I can just tweak everything down and then just beat this robot. And on the days that I'm feeling very challenged, I can make them just a little bit better than me. If you play individual sports, you know that you want to play with somebody who's just, about the same level, maybe a little bit better than you. So that's what I really wanted to build. It just had legs, it could run around and do everything. So I even went to, grad school building robot, still thinking I wanted to build this tennis robot for myself. So this is what I did for my at MIT. This is a robot called COG, stands for cognition, and then this was initiated by Rodney Brooks in 1993. And then I built the arm and hands for this, and the whole idea was to spend 5 years of graduate students' time to build a 2-year level of cognition. It's been about 15 years, and I don't think it's at 2 years old yet, but we are, I'm sure they'll keep working on it. What I did for the hand part was that I basically before the whole robot was ready, I put the hand on the stick and walked around in the lab, starting from just a simple baby reflex. Babies when they're born, you touch them and then they curl their finger around you, and then you do something and, tickle and then open up. That's all I hardwired. Everything else was a learned process. So by just curiosity, babies just bump into it, have reflex, and then touch something and say, oh, this was interesting. I just had some behavior that I like. That's kind of how they learn, and that's exactly how I start to build this mechanism to learn to grasp objects. This went really well, it turns out, and I was able to pretty much walk around in the lab and grab just about any object using this robotic hand. And I thought, okay, great. But the next thing I wanted to do was some complicated dexterous operation as we are involved in. And I stumbled on many problems that I just could not do. And I thought at that time, the reason I can't do it is because we, as a field of robotics, we don't understand enough about neuroscience, how human brain controls these motion. We do this without really thinking a whole lot about it. But if you ask any of the roboticists and any of the robotic hands to just do something like this or spin a pen, something relatively simple that we do, none of the robotic hands can do it. And I thought, well, I just have to crack that secret code inside our brain. So I jumped off the robotic ship, went into neuroscience, and then my PhD thesis really looked like neuroscience at the end. And, well, I didn't quite solve that problem, but I certainly gained some background in neuroscience. And when I was ready to combine them to move toward building a tennis buddy, I was not that interested in building a tennis buddy anymore. I'm still interested a little bit. But by then, I really sort of got taken by learning neuroscience, how many people are disabled because of some neurological disease. And knowing robotics, I really felt like there are so many things that I can do for those people who are neurologically disordered, stroke, Parkinson's, many things I started to think about. So instead, I still combine neuroscience and robotics. But I sort of start to envision something a little bit different from the tennis buddy. Those are two things that are toward combined neuroscience and robotics to help people. One is replacing body parts with robotic device and controlling that from the brain. That's what, the moment I say I work on neurobotics or combined neuroscience and robotics, this is exactly what people always say that I must work on. I said, oh, you control prosthetic device from the brain. Sure, this is one of the things that I do, and then I will talk about this specifically related to the hand today. But also, I don't want you to forget I actually have yellow box. Here you go. I didn't want to also forget to mention that neurobotics does not have to be invasive in the way that's described here. We don't have to put chips in your brain. We don't have to replace your limb. If you wanted to have a neurobotics experience, you could actually do this as a completely non-invasive system where you sit in front of the robot, as this guy's doing over here. The moment you hold onto a robotic device, we can have a nice program which can extract some of your neural signal simply from observing your motion and sometimes some of your muscle signals accurately. Those things, and I'm give you some perturbation, we bump your arm a little bit and then we measure how you react to those things. And all those things can give you so much information about the human brain and the current state that we don't really have to drill a hole and then put a chip in there. So that's another way that we do work quite a lot in the neurobotics field. So as you're listening to my talk, I don't want you to think that I drill a hole in the brain all the time. This is sort of, every time I gave a talk, everybody said, oh, what you work on seems like the one from the Star Wars. So eventually my grad student said, why don't you just show that clip every time you give a talk? So here it is. And this is really what I'm after. So trying to understand the brain enough that we can replace a limb when Luke Skywalker loses the arm fighting Darth Vader, and his hand, that looks just like his hand, but inside is all mechanical system that's controlled as he's thinking about moving his fingers, they move naturally. Hollywood could visualize this in the 70s. We are still struggling to do this in real life, but we're making progress toward it. Before I jump into discussing sort of how you combine those or how we go about progressing in this field, I just wanted to tell you a little bit about the human structure. I know that many of you are great scientists, but you might not be as familiar with how the information flows occurs in the human brain, the human body. So the moment you think about, I want to tap on this corner, the brain thinks about this abstract information, and that's all in the sense of electricity current that gets propagated into more of a muscle-like signals through spinal cord and then goes through the nerve and then eventually reaches the muscle, all electrical signals so far. Then the electrical signal beautifully gets converted into force, this positional displacement and maybe even stiffness change at the muscle through the chemical reaction. And then that moves our joints, and that ends up affecting the external behavior. This is sort of the extremely simple level, but this is how the movement information, the command from the brain propagates to the actual task. Then we have feedback like skin feels something, we see something going on, tapping, and then those information corrects or augments some of the motion that's being made. Now, turns out, robot is not so different from human system. This is exactly why we can talk about replacing some of the body parts with the robotic system. So the brain, I'm not saying that we can completely replace your brain with a computer, but the function is quite similar in terms of the computer. Computer operates with electronics that has current going through it. And if we wanted to control a robot, we put wires that come out of it with the commands, amplify the signals that goes into the motor. Current signal gets converted into torques and joint angles and stiffness changes that affects some metallic joints, and then have sensory feedback. And turns out this is really how robotic internal control flow looks like. So now you can imagine if they look this similar, what you can do is to start from a human who might have just had some trauma, maybe got in a car accident, lost a limb. We can talk about replacing that with a robotic limb, and that's exactly what this guy is like. So these are people, this is a courtesy of the Rehab Institute of Chicago, and they are people who lost arms in accidents. He's a very famous poster child, Jesse Sullivan, who lost both arms in an electric accident. And he basically had a surgery done to the nerve that used to go to his arms to be penetrated into the pectoral muscle, the chest muscle. So as he now thinks about moving the thumb that he doesn't have anymore, the chest muscle actually twitch. This is a surgery that was done. It's called nerve reinnervation. And now if you have muscles wired up, muscle is an amazing, beautiful biological amplifier, better than taking just the nerve raw signal and then trying to amplify that using electronics. So this is sort of the beautiful part of the science. And then once that's visibly, that's something, the electrical signal that you can extract on the surface of the skin, you can put electrodes on that pectoral muscle and then just say, okay, now try to move your thumb. Muscle twitching, the electric signal is detected on the chest, that patch goes to control the robotic thumb. Okay, so that's a really nice work. And then that's, nice neural control. As he's thinking about moving his original hand, he can move the robotic finger. So this work is great. And I even have a video of him operating his arm. This is really probably the first time that any prosthetic hand or arm multi-joint system have moved together. There are some robotic or prosthetic limbs that can go shoulder, elbow, wrist, and one joint degree of control at a time, but he is making actually multi-degree of freedom control at the same time. I want to also tell you, though, that, of course, this technology is only 3 to 5 years old. We're making dramatic difference in this field within really the last, few years. This is pretty amazing. But unfortunately, at this point, this is brand new field. Resolution is limited. How many bits can you get out of the surgery? Maybe we can actually get about 6 at most information. 6 meaning that maybe our arm actually has 7 degrees of freedom, meaning the shoulder can go up and down, side and side, and twist. Elbow has 1 degree of freedom that can go like this. All those times you can kind of think of it as individual, control bits that you have, like if you had a Wii and then you had how many buttons do you really have to have? So that's that. In terms of that, they can get about 6 of those knobs at most, at best. Our hand naturally have about 22 degrees of freedom. So we're nowhere near being able to get this sophisticated control from this idea. Also, this technology can only be available to people who had, amputation, not people who have spinal cord injury or anything higher up. So if you imagine some people who actually have had spinal cord injury, what we would do instead of replacing the limb would be to maybe build a robotic exoskeleton for you, which is a wearable device. And the rest is we have to somehow bypass the injured part of the body So we extract the signals directly out of the brain. This is the part about drilling a hole. And then put that electrical signal into the computer, and then somehow process it and then bypass to control the robotic device, which would in turn control the limb. And this is a technology that a company called Cyberkinetics in Connecticut has offered, which is was tested on humans a couple times. There's a chip that goes into the brain, and then chip meaning like actually electrodes coming out, going into the tissue. Wire come out and then go through a port on the skull, and then the actual external wire comes out. In this case, what the video shows, and then this is exactly what they've done, was for people who are absolutely unable to move a single muscle intentionally, but they have healthy brain inside. Lou Gehrig's disease, many disease can cause this type of disability. But what if they can just think about moving a cursor on a computer screen up and down, side to side, and then make that realization? Then we can put keyboard on the computer screen, and they can move and then type the intention. Are you in pain? Yes. Those things that they cannot do at all right now. So this would be a great breakthrough. And at this point, that's extremely primitive. As I said, there are about 2 human subject trials that have gone on. There are some animal trials that are going on. But that's the extent in terms of the human trial. Now, this is my collaborator at University of Pittsburgh, Dr. Andy Schwartz. He is pushing the envelope of this field using monkeys. And what this monkey can do is that he was trained to reach for food that was presented in a 3-dimensional world. During that time, his brain signal was recorded and found a correlation to where the food was presented or the movement velocity and direction, and for the brain signals. And once that correlation was found, they strapped his arm under the sheet and then ported that same information to control this robotic arm. So now he sees the food, he thinks about moving his own arm to move toward the food, and that signal is being used to move the robotic arm toward the food location, and he can feed it back to himself. Okay. So this is really state-of-the-art. This is about as much as we can do right now. And in terms of the hand open and close, at this stage, this video was taken probably 3 years ago, 2 years ago. At that point, the hand was actually, hand open and close was something that we couldn't get the signal, or they couldn't get the signal, so therefore the grad students were sitting there with a remote control to control that open and close. And the most recent story from the New York Times have said that they don't actually have to even control it. Actually, the animal has learned to use the already open hand and stab through the food to get the food and feed it. So it's kind of interesting. But talking about the hand, I'm going to now take you down in this narrow rabbit hole of neurobotics and then onto prosthetic hand and then sort of the human dexterity and so forth, and we'll pop it back out. But I wanted to sort of pay really attention to what people are using, in terms of the prosthetic hand right now. And they're extremely primitive. The nails might be painted, but they're basically, just a glove that looks like her own hand, but function is extremely limited. It could just open and close. And even with that, it's so clumsy to use that after I think he gets paid to use or have this arm on for like 3 hours a day or something like that. After those hours are done, he pops his hook right back on again. Why is that? Because this is somehow too clumsy. The usefulness is not there enough to make it worth it for him to just keep trying it. So, what's wrong with it? Well, here are the very advanced prosthetic hands that are available in the market right now. The hand can do open and close. Sometimes you can do thumb motion. This is also a very famous company, Autobot. They do a great job. They also can open close. This is a new company. They just started selling a limb called iLimb. If you are a YouTube kind of person, you should just type in iLimb and see. They have really awesome videos. But what they can do is move the individual finger, 5 fingers like this. Thumb cannot go like this, so somebody has to move the thumb like this for externally to make this happen. But still quite nice. But that's sort of where things are, because we have to package it up so small, so light, that people won't get discouraged immediately in terms of wearing it. So this is primitive. Many of you probably know about the DARPA initiative. DARPA has this initiative called the Revolutionizing Prosthetics. They have poured in, I think, up to date about $75 million, I think, to really make the hand prosthetics to be as dexterous as possible. They now, I think, have 19 degrees of freedom in the robotic hand, their prosthetic hand, and making it as light and, easy to use as possible. But all of that sort of falls into even the DARPA hand falls into a little bit of this category of the problem that robotic people keep having. I'm coming from the robotics field, and most of those hands are something that I've been involved in or owned or designed. So I'm going to criticize all those hands a little bit, but I think they're all great. So I just wanted to put a disclaimer up front. Anyway, so people have been building robotic hands for a long time, for about maybe 25 years, and doing an amazing job. Even 1983 hands, the Utah MIT hand, it's something else. This hand had fingers with all the corresponding joint angle motion with 4 sensors at the fingertip, controlled by maybe 2 refrigerators full of large controllers at that time. Really what changed in the 25 years is not how the hand looks like, but how big the controller is, or how fast the controller, how fast we can control the hand at this moment. But all those times that roboticists have been fascinated with building hands to pursue this human dexterity, none of them have been really able to get there. It's so difficult to understand what is missing, and why is it that we keep building over and over, spending millions of dollars building hands that's, again, going to look something like that again, and then just not do anything. So one of the things that I've noticed as I was studying my own hands that I've built to other people's hands is that we kind of engineers get constrained by the external irrelevant constraints. Like, we have 22 degrees of freedom. We got to build a hand that has 19 degrees of freedom. We got to build it. Or, then they say, but let's just compromise that palm flexibility. That doesn't seem important. Have 5 fingers. We got to have 5 fingers, or else it's going to look like Simpsons Family. We can't get away with that. So, they're basically sort of somehow the constraints set ahead of time by the engineers, and then those things might not be set right. So, as I said, in terms of the palm inflexibility, if you see most of those robotic hands, palm is not flexible. Imagine if you have to grab a bottle of water, trying to drink this thing with your rigid palm. It's very, very hard to do. Okay, so those are the kind of things that I feel that we kind of have to step back and say, wait, time out. We're not looking at the right salient information that humans utilize to build hardware system that has to go into the future prosthetic device, or even just simply robotic telemanipulation device. Because the moment we give this hardware to the software, people said, okay, now control it. If the mechanism itself doesn't contain the salient features of the human system, they will never be able to control it in the right way. So that's really there are 2 points of tackles to tackle, which is, I'm going to actually skip that one. One is the hardware aspect. Can we actually try to understand the musculoskeletal details of the human system, trying to extract that, something, secret sauce. I'm going to actually call that. Okay, so secret sauce of the human hand. Can we actually, understand that in the hardware? And given we understand that, now can we actually look at the control signal that arrived to this system? And once we can really start to understand it, then we can say, okay, then what is it the thing that is contributing to the human level dexterity? Then can we actually try to help people? Okay, so that's really the approach that I'm making. Turns out, if you look in the literature, even biomechanics, so forth, many of those information is not available yet. So even for me to pursue this direction, I ended up dissecting a lot of human hands myself just to gain this knowledge. And all these people have contributed to this project or in our lab so far. I was just adding a bunch of pictures and I started to run out of space, and I'm crawling up. Next time I see you, maybe this page will be full of faces. And in actually 2002, after, again, going through in just a whole bunch of human hands to understand some of the things that does not exist in the literature, we have come up with a prototype of what we thought had contained the salient features of the human system. We have mimicked the bone shapes. We have mimicked the tendon routing. And we collaborated with 2 hand surgeons and an animatronicist who was building basically dinosaurs for the Jurassic Park movie. And those guys are amazing, actually. If you're one of them, please let me know, because he built this hand in like 3 months. Wow. And then worked for 6 weeks straight in a museum. That just really impressed me. So that was really great. It worked 9 a.m. to 4 p.m. every day in a museum, typing keyboard. It was very impressive. But towards the end of those series of weeks, the control became really difficult to do. Fingers start to move really slow, really hard to control. So we got the hand surgeons to come in and evaluate the hand and said, well, what's wrong with this hand now? And he just moved around and said, well, I'm sorry, but your robotic hand has developed arthritis. So we basically reached a point where we were overusing it, and the joints were wearing out. And that joint turns out to be extremely difficult to mimic with the current material science knowledge. Joints, human joints are basically 2 bones come together. This liquid called synovial fluid surrounds it, and then encapsulated by ligaments, and then it's just extremely frictionless. But there's just no such thing, well, at least within the cost that we can afford, that we can actually build. Whenever I say there's no such thing as the artificial synovial fluids, I always get an email after that talk and says there is. It's just really expensive. So apparently it does exist, but we didn't know, and then it seems very expensive. So anyway, so that's what we found out. So after this process, what we found out was that we can go like crazy, mimic a lot of different features, but really what we want to be doing would be to sort of mimic or understand as much of the salient features as possible while we still try to produce within the current constraint of material science what functions. So over time, since 2002 till 2009, we have iterated and iterated and iterated without building the entire hand because that was too much. So we just built different index finger over and over and over and over. To the point that at some point we said, you know what? Maybe we have it. We actually are pretty happy with our current design. It's not falling apart over repetitive use. Maybe this is the way to go. So we designed and then went the whole shebang, and this is what we have in our lab. So we were finally assembled. 3 fingers are actuated. There are 5 fingers. 2 fingers are not controlled. System attached to a robotic arm with all the motors that are simulating individual muscles. So one muscle, it has, because the tendon routing is basically the same, each muscle is equivalent of a muscle. And all of that resides in the forearm. So this is what we built. And we don't have a picture of the video of very recent video, but this is taken with, just to show you how fluid the motion is for our robotic device compared to probably many of the robotic devices you've seen. So my goal is to, when people say, even my kids, when they make a robotic motion, they go like this, right? It's like, come on, we can do fluid like this in the future, so hopefully that's going to go away. But anyway, so turns out if you mimic quite a lot of the biological features, you can do the motion a lot more fluidly. The movement that you saw here on the hand side, that's driving this finger. So you can record the human movement, and you can port that over and then display that on a robotic system. So going through this whole motion, now you're thinking, well, when's this prosthetic device going to be available? I'm not quite going that way yet. I'm really still in the science component. So far, I feel like what I've really been trying to tackle on is the biomechanical complexity. Again, what's the salient feature of the biomechanical system? Trying to answer a little bit of that. And then trying to figure out, okay, so given those are the structures, what is going on in the control signals? And I'll tell you a little bit about that for the next 10 minutes. Okay, so one of the things that we did was to mimic the tendon routing of the human finger. Turns out, if you peel off your skin from the finger and then look at it, tendon routing is extremely complex. And so complex that this is an extremely simplified model that's available in a biomechanical literature. But even with that, that's lots of connections. One of the things we wanted to find out was, are those connections there because it's an evolutionary baggage? We were ducks or whatever that we might have been, and then because of that, connections are there. We just happen to carry it over. Or maybe it's a marvel. Maybe we actually have, resolved over time that those are indeed the important ones to keep on. We tried to answer that question, and we, as engineers, we were hoping that simpler the better. So we were hoping that lots of connections that we end up finding out to be useless. Unfortunately, that's not what we found out. Turns out our index finger has all this motion, and if you try to build a robotic system that can do the same thing with simple connections that are not interconnected like that, it requires 8 muscles to realize this motion. Humans do it with 6 muscles. And that's because of those interconnections of the tendons. So that's pretty nice. Well, that's unfortunate from us building a point of view because it's really hard. Actually, the most recent thing, as of almost 2 weeks ago, a new grad student I took on, he decided the best way to build this, we've been building with nylon and then rubber coated, all those things, and then he decided that crocheting is the way to go. So he now actually takes the smallest nylon wire with the smallest gauge crochet tip, and then he just crochets this whole tendon head structure. It's really amazing. Anyway, the moment we actually have this complex web of tendons, we actually found out that the timing of the muscle activation matter. Because those 6 muscles are acting like 8 muscle structure, so some of the muscles are now redundant. So if you activate ABC in the order of ABC, you end up here. But if you activate in BAC, you might end up over here. So that's interesting. That's posture-based control. And the moment that we have the tendons routing to be the same or similar to human system, the bone shapes start to matter. Because if we're going to guide those tendons that are sort of going over the bones, the moment arm, or the affected force that gets applied to each link on the robotic finger, the links gets different. Imagine if you put a big ball on each joint, suddenly you pull on a little force on this side, and then you get big force on the other end. So we wanted to, as roboticists, it's much easier to come up with a cylindrical joint structure, as most of the robotic fingers are. So we really wish that this is going to be the best way to go. But turns out, the moment that we mimic the tendon routing, the bone shapes were important, to the point that we found something very interesting. And this is pretty recent data. We found out that because of our asymmetry in the bone shape, it allows us to basically hold an object held in the center of our palm with the least amount of energy from the muscles. And that's just coming from the bone shape itself. We didn't know that. That's pretty cool. But now suddenly we have to mimic all those crazy shapes of the bones. So that's why our hand looks so complex so far. But anyhow, so those are the kind of the biomechanical contributions that we're starting to make using our hand. So by simply building it, stumbling upon things we didn't know or we don't know, so we say, well, let's figure it out. That's really the approach that we've been making. So even though the progress seems like it's been slow building the system, we feel like we're enjoying this process because we're learning a whole lot ourselves and we are making contributions in science. Here's neural control side of aspect. So this is for people who like optimization. This would be it. But so brain has lots and lots of neurons, and then that eventually controls maybe one force contact point, and that's all it matters. So there's this extreme amount of redundancy in how our brain controls a certain task. And we wanted to find out how the human system choose out of all this potential redundant system a certain solution, certain strategy that is being used. So we actually specifically looked at the index finger. Index finger alone has 4 joints or 4 degrees of freedom, meaning that 1, 2, 3 joints, this knuckle moves up and down and side to side. So that's the 1, 2, 3, 4 counts, controlled by 6 muscles. Actually, you have 7, but 2 are redundant, so let's call it 6 muscles. And that combination of 6 muscles controlling 4 degrees of freedom have this redundant space of this 2-dimensional redundant space. So this is an extremely abstract 2-dimensional manifold that lives in this 6-dimensional world. So you can't visualize it until somebody, mathematics guys, came over and said, you can use this thing called a manifold learning. Okay. I don't know what it is too well, but except I can run the algorithm to visualize this 2-dimensional system that resides in this 6-dimensional thing that none of us can visualize, and blast it onto a paper, and the green blob that you see is basically that. So we have, in order to execute one specific force out of a fingertip and a specific stiffness of the finger, turns out there are infinitely many different ways that we could do this from our brain, or in terms of the controlling the muscles. And out of those solutions, which one actually are we really picking to operate? And good engineer might say, we must be minimizing energy. That must be one very important thing to do. And we thought the same, and that's exactly what we looked at and says, is the biological system minimizing energy as we operate through the space that has many, many different ways of doing it? Turns out the answer is it doesn't seem to be it, at least for the hand. Legs, it might be, as running for a long time, weighing, taking on a lot of weight. Maybe those are more important for saving energies, but fingers, maybe it's not as important. And we're still in the process of this. So we plotted basically all those infinite possibilities of neuronal solutions, and then we recorded from human muscles by getting great subjects who were able to bear 60 needles stuck in their muscles and then recording from it. And we found that the biological signal, if you record from any subjects, they all seem to cluster in right about the same spot. So they all seem to be optimizing likely on the same criteria, but we don't know for sure what it is. What we found to be the closest so far to explain it is that we seem to somehow maximize the utilization of small muscles and minimize the utilization of big muscles. Yeah, we said the same thing. We said, So we don't know why that is. And if you tell that to an ergonomist, they tell you that, that's really a bad idea. Overstraining the small muscles and just relaxing the big muscles is exactly the way to get injured. But that seems to be something that we are doing with our hand, and we want to sort of keep pursuing and says, why is that? Is that just an artifact of something else, or is this actually useful? And therefore, we actually get injured, carpal tunnel, many things that can occur with our fingers. So that's very interesting. And we are indeed drilling holes into people's brain and recording and using signals, or at least extracting signals. But it sounds, I just made it sound kind of as worse than it is. But so this is called ECOG. This is people who have epilepsy. They have, if they have it so bad and seizures occurring all the time, they go through a procedure. They go to the hospital, open up a skull, put a mesh of sensors, which you can see white little dots in there, and they sit there in the hospital and wait for the seizure to occur. And the moment seizure occurs, they know where the seizure was coming from. They go in and come up with a treatment for that location. But turns out, while the patient has this grid sitting in the hospital, they're pouring out this incredible amount of brain information that could be correlated with some behavior. They might be scratching, doing something, eating. We could suddenly, if we are allowed to correlate those signals, there's a whole lot of neuroscience that we can do. And that's exactly what this is. So we are not implanting those sensors for the sake of controlling prosthetic devices, but we're just learning as we tell them to move index finger, as we tell them to move the pinkies, and then looking at the activities, can we actually correlate those signals? And then these wiggly lines are what those, if you just one of the electrodes is recording in current. This is pretty much sort of filtered signal coming out of the brain. And the smoother line is the information coming from a glove that the subject is wearing, recording the joint angle motion. So turns out, and then I think some of them are index fingers, some of them are thumb, and so forth. So turns out you can actually find some correlations with the motion that people are making with the individual fingers in some of those individual nodes that can be found right on the surface of the brain. So there's a lot to investigate here, and that's, again, sort of the state of art of this field. So I'm going to pop back up to tell you that we just went through a very small rabbit hole about this prosthetic hand and human dexterity direction, which is the top part of the neurobotics as a field. And even within my lab, the neurobotics lab, we work on quite a lot of different areas. Some of the flavors I didn't tell you are in the robotic rehabilitation. So again, the field of, we don't actually tap into the system. We don't actually replace limbs, but somebody who just had an injury, stroke, we can rehabilitate their motion that's beyond what they might have achieved on their own because we keep track of the neural state. And then we do this in a combination of robotic and virtual reality environment. And I can tell you a little bit more about that some other time. One thing I also wanted to really mention was the Neurobotics Lab has effect or impact in many, many different fields beyond what you might have thought about. So we talked about scientific discovery, rehab, assistive technology, but we can actually do things like, disease prediction, prevention. The same robotic environment have been shown, this is not shown, but a postdoc who I had in my Ph.D. lab have shown that disease such as Huntington disease, which is a cousin of Parkinson's disease, the onset can be detected by the robotic device far earlier than the clinical onset. So now the possibility is big. If you had, there's no such thing right now, but if there is a pharmacological system, the intervention that can slow down Parkinson's disease, say, then detecting that early on will have a huge effect. Right now, that medicine doesn't exist, but they start to be showing that exercise will slow down the effect of Parkinson's. So, again, detect it early, put you in an exercise paradigm, less Parkinson's effect, lots of good things can occur. That's really interesting. We talked about ergonomics, evolution. Of course, space exploration. NASA would love to have a hand like this, go up in Mars, not have people exposed to the radiation, go and, humanoid go and turn over a rock and then see if it's a little bug underneath it and, all those very dexterous operations they love to do. So again, we can contribute to that. Computer graphics, all those animations that, maybe your kids go and see that are starting to look more and more human-like. All of that field and our field are all connected. Next time you're sitting on those animation movies, see how those animation characters' hands are moving. You probably don't pay attention a whole lot about it, and they often simplify it with a little fist, maybe, but they're not great yet. But, again, the kind of things we find may also help those graphics. So, lots of different effects. We also, in our Seattle area, we started what's called a neuroengineering center. Neuroengineering is even bigger than neurobotics. Neurobotics is a subfield of neuroengineering, where we basically say all engineering, physics, math get together and then marinate with the neuroscience for the purpose of understanding and then to restore some of the brain function. And we are actually really building this up right now. We had a pretty big workshop. And then if you want to find out more about that, that's the webpage neuroengineering.washington.edu. In general, I'm going to start to sort of go more personal direction than I think Susan also had in my introduction, saying that I was planning on starting a nonprofit. I started it. This nonprofit, the motivation came from the outreach that I was doing as part of my NSF project. NSF, if you've written grants for National Science Foundation, you might know that we also need to not only talk about science, but how we're going to have broader impact in people's education. And that's something that I've always had passion in, and then I've always written in saying, well, I really want to somehow recruit more kids by combining this disabled kid population, making into a team, and then all of them have to come up with some sort of a solution together and then build it and provide it and then test it. So that's what I've been doing, and it's really fun and successful, rewarding for everybody. And as a process, some of the disabled kids are starting to think, engineering, that's an interesting field. That only helps our field to have them to actually brainstorm with us about what the right thing to do are. Also, turns out the moment we say we're going to help people through science and math, girls look and say, oh, I don't have to become a nurse. Okay, I can kind of go into engineering. I am kind of good at math and science. And that's been really a great tool for recruiting. And also some of my very young undergrads have ended up producing journal papers. So it kind of has all the great nuggets that come along with it, and we've been happy with it. So for my nonprofit, I've been doing this on my side, again, from my own personal money to NSF small amount of grants. And now I wanted to do this on a larger scale than like one per year. So and the nonprofit idea is not only I work with undergraduates and some high school students to build the devices. Now we actually, on this team, we also have women who have given up potentially their career to optimize on their family for a little while, and coming back and thinking maybe what they really want to do, and it's not just women, by the way, but they're thinking that maybe what they want to do next would be to have some contribution to society in a way that they haven't felt like they've been making. So we have that team added here, and now with this nonprofit starting to run, we're starting to take on test cases, looking for funding. That's kind of, it's going, and it's kind of exciting right now on that. And this is likely sort of my last slide, just to show you that I have sort of the 4 quadrants of things that I constantly go through in my mind. Every morning I wake up and I actually look at this chart and say, okay, these are the things that I want to make changes in the world. I want to somehow provide robotic assistance now in a way that other people are not able to. And am I doing a good job recruiting all those people who can be benefiting, who can become scientists, engineers? Cheap way to put my family photo, but besides that, I'm very interested in assisting women to be able to do things like this. Now that I'm doing it, it's so darn hard. It goes, of course, not just for women, but the moment you have kids, you didn't realize how hard it is to do all those things. Your husband or wife tells you, like, you can go on this trip. It's all those things happen all the time, and then there got to be ways that we can start to change that. I'm really interested in that. And finally, with this growing population and aging population, I want to create an environment that's rich as we all grow older and then just want to be learning more. We're not just learning for my sake, but maybe contributing some sort of an outlet to do that. So those are sort of the things that I keep thinking about as I move my research forward, my personal life forward, and I'm trying to now start also a nonprofit on the side. So thank you very much, and here's the webpage, if you would like to know more.